An ultrasound device is a sophisticated piece of medical equipment that uses high-frequency sound waves to create images of the inside of the body. Here's a breakdown of its main components. Transducer probe. This is the part of the ultrasound machine that comes into direct contact with the patient's body. It sends out sound waves and receives the echoes that bounce back from the tissues. The probe contains piezoelectric crystals that vibrate when an electric current is applied, producing sound waves. These crystals also convert the returning sound waves into electrical signals. Central Processing Unit, CPU. The CPU is the brain of the ultrasound machine. It processes the electrical signals received from the transducer probe and converts them into visual images. It also contains the electrical power supplies for the machine and the transducer probe. Transducer pulse controls. These controls allow the operator to adjust the amplitude, frequency, and duration of the pulses emitted from the transducer probe. This is important for optimizing the quality of the image display. The processed images are displayed on the screen, providing real-time, dynamic views of the internal workings of the body. Keyboard/cursor. This is used to input data and take measurements from the displayed images. Printer. It prints out the images generated by the ultrasound machine. The transducer probe is a key component because it determines the field of view and the depth of penetration of the sound waves, which affects the resolution of the image. The shape and size of the probe can vary depending on its intended use, such as for abdominal, cardiac, or transvaginal ultrasound. The ultrasound machine operates on the principle of the piezoelectric effect, where the application of electricity to the piezoelectric crystals in the transducer probe causes them to vibrate and emit sound waves. When these waves hit different tissues, they are reflected back at different rates, creating echoes that are then captured by the probe and transformed into electrical signals. The CPU interprets these signals to produce an image that is displayed on the monitor. This technology is widely used in various medical fields, including obstetrics, cardiology, and radiology, due to its non-invasive nature and ability to provide real-time images without the use of ionizing radiation. Let's delve into more components of an ultrasound device. Pulsar/transmitter. This component generates electrical signals that the transducer converts into ultrasonic pulses. It controls the timing, strength, and duration of the pulses that are sent to the transducer probe, receiver. After the transducer probe picks up the echoes, the receiver processes these incoming signals. It amplifies, filters, and demodulates the echoes from the transducer. The receiver's functions include rejection, amplification, and compensation, which help to refine the signal for better image quality. Memory. The ultrasound machine's memory stores the processed images and video sequences. This allows for later retrieval, analysis, and comparison with subsequent images. Digital signal processor, DSP. The DSP takes the electrical signals from the receiver and converts them into a digital format. This digital data is then used to form the image displayed on the screen. Display modes. Ultrasound images can be displayed in different modes. A mode, amplitude mode, displays the amplitude of echoes as a function of depth. It's mostly used in ophthalmology. B mode, brightness mode, translates the amplitude of the echo signals into brightness on the screen, forming a two-dimensional image. M mode, motion mode, tracks the movement of structures such as the beating heart by displaying the amplitude along a single line over time. User interface. This includes a keyboard and a set of control knobs or a touch screen that allows the operator to interact with the ultrasound system, adjusting settings and capturing specific images for diagnosis. Disk storage devices. These are used to store the acquired ultrasound data and images. They can include hard drives, compact discs, DVDs, or flash storage devices. Power supply. Provides regulated power to all components of the ultrasound machine. Printer. Some ultrasound machines have integrated printers to provide immediate hard copies of the images. Alternatively, images can be sent to a network printer. Network connectivity. Modern ultrasound machines can connect to hospital networks for the transfer of images and reports, allowing for integration with electronic medical records, EMR, systems. Each component plays a crucial role in the functionality of an ultrasound device, ensuring that it can capture clear images for diagnostic purposes. The technology behind ultrasound is constantly evolving, leading to improvements in image quality, portability, and functionality. Here are additional components of an ultrasound device that contribute to its functionality. Scan converter. The scan converter translates the ultrasound data from the beam spatial format into the format of the display screen. It also stores the image data in memory, which can be manipulated to change the image before it appears on the display. Acoustic lens. This component focuses the emitted sound waves from the transducer probe. It ensures that the waves are directed to the precise area of interest within the patient's body. Gel. A special conductive gel is applied to the patient's skin where the transducer probe will be placed. This gel helps to reduce air pockets between the probe and the skin, which can interfere with the sound waves transmission into the body. Control panel. It includes various knobs and switches that allow the sonographer to control the behavior of the ultrasound machine, such as adjusting the depth, gain, power, and other parameters to optimize the image quality. Image processing software. Advanced software algorithms process the ultrasound signals to enhance the quality of the images. This can include noise reduction, edge enhancement, and other digital processing techniques. Doppler unit. In machines equipped with Doppler capabilities, this unit measures and visualizes blood flow within the body. It can display blood flow in different colors on the screen to represent the direction and speed of the flow. Speakers. In Doppler ultrasound, the speakers allow the sonographer and patient to hear the sounds of the blood flow or movements within the body. Foot switches. Some ultrasound machines have foot switches that allow the operator to capture images or perform other functions hands-free while maintaining probe contact with the patient. Battery backup. Portable ultrasound machines often include a battery backup system that allows them to operate without being plugged into an electrical outlet, which is particularly useful in field settings or during power outages. Cooling system. High-performance ultrasound machines generate a significant amount of heat, so they are equipped with cooling systems to prevent overheating and maintain optimal performance. Ports for peripheral devices. These ports allow for the connection of additional devices such as external monitors, recording devices, or printers for expanded functionality. Each of these components plays a specific role in ensuring that the ultrasound device operates efficiently and provides high-quality diagnostic images. The integration of these parts allows for a wide range of applications, from pregnancy monitoring to cardiac and vascular imaging. Here are some advanced components and concepts related to ultrasound devices. High-voltage multiplexing. This is used to control which transducer elements are active and to direct the high-voltage pulses from the transmitter to the appropriate elements in the transducer array. High-voltage transmitters. These generate the necessary high-voltage pulses that drive the transducer elements. The voltage level of these pulses determines the intensity of the ultrasound waves. Image path receivers. After the transducer receives the echoes, the image path receivers amplify and process these signals so they can be converted into a digital format for image formation. Digital beamformers. These components are responsible for steering and focusing the ultrasound beam by controlling the timing and amplitude of the pulses sent to individual transducer elements. This is crucial for creating a clear image. Beamformed digital signal processing. After the beamforming process, the digital signals are further processed to improve image quality. This may include dynamic range compression, filtering, and other signal enhancement techniques. Display processing. This involves converting the processed ultrasound data into a format suitable for display on the monitor. It includes scaling, color mapping, in the case of color Doppler imaging, and other image adjustments. Piezoelectric effect. This is the underlying principle that allows the transducer to convert electrical energy into mechanical energy, sound waves, and vice versa. It's fundamental to the operation of ultrasound devices. Phased echo concept. This refers to the technique of using the time delays between the received echoes to construct an image. By analyzing the phase differences of the echoes, the device can determine the location of structures within the body. Spectrum waveform. In Doppler ultrasound, this is a graphical representation of the flow velocities within a vessel over time. It helps in assessing the nature of blood flow and detecting abnormalities. Color Doppler. This technology assigns color to the direction of blood flow, which helps in visualizing and assessing vascular structures and patterns within the body. These components and technologies enable the ultrasound device to provide detailed and dynamic images of the body's internal structures, which are invaluable for diagnostic and therapeutic purposes in medicine. General overview of some additional aspects that might be involved in the operation of an ultrasound system. Electrical filters. These are used to process the signals received from the transducer. They filter out unwanted frequencies to improve the quality of the diagnostic images. Switching systems. These systems manage the electrical connections between the transducer elements and the rest of the ultrasound system. They ensure that the correct elements are activated at the right times during the scanning process. Data acquisition systems. These systems collect the raw data from the transducer. They often include analog to digital converters that prepare the data for further processing by the CPU. Thermal printers. Some ultrasound machines use thermal printers to produce hard copies of the images. These printers work by selectively heating coated thermochromic paper, elastography software. This is a relatively new technique that measures the elasticity or stiffness of tissues, which can be helpful in diagnosing certain conditions. Contrast agents. These are substances that the patient may ingest or receive via injection to improve the quality of ultrasound images. They work by increasing the reflectivity of certain tissues or blood. Biopsy needles. In procedures where a biopsy is needed, some ultrasound devices can guide biopsy needles to the precise location within the body. 3D/4D imaging software. Advanced ultrasound machines can create three-dimensional and even four-dimensional, 3D over time, images for more detailed examinations. Wireless transducers. Some newer models have wireless transducers that allow for greater flexibility and ease of use. During the scanning process, portable power sources. For portable ultrasound devices, lightweight and long-lasting batteries are crucial for use in various settings, including fieldwork or bedside examinations. Quality assurance tools. These are built-in or external tools used to regularly check the performance and calibration of the ultrasound machine to ensure it is functioning correctly. Security features. With the increasing connectivity of medical devices, security features are important to protect patient data and ensure compliance with health information privacy regulations. User training materials. Many ultrasound systems come with training materials, such as manuals or interactive software, to help users understand how to operate the machine effectively. While these components and features may not be present in all ultrasound devices, they represent the ongoing advancements and the diverse capabilities of modern ultrasound technology.